Okay, so we had some practice problems and for chapter 8 that I hope that you will be able to use as a good review for preparation for your first exam with chapter 8 concepts. If you have any trouble or questions with any of this content, I strongly suggest that you visit my office hours and let's identify where your problems are coming from and see what we can do to help to improve your understanding. Okay, so with each one of these questions, what I'm going to do is I'm going to do a few of the examples for each one. So for this first question, it asks us to write the orbital diagram that represents the ground state of selenium, titanium, silver, bromine, helium, manganese, barium, the chlorine, the chloride ion, the sodium ion, the sulfide ion, and the aluminum ion. So what I'm going to do, I'm going to do the selenium atom, the chlorine ion, and the aluminum ion. So first let's remind ourselves of what our rules are. This periodic table doesn't have any numbers on it, so I'm going to go ahead and put our numbers down. We know that when we put electrons in orbitals, they have a certain order that they fill in. We've got that little chart that looks a little bit like this, that we said that if you're on an exam and you need to reproduce that, you could always draw your own. Remember the one from the notes that looks like that? So that we can generally predict our order of filling for our electrons. So we know they go in order of lowest energy to highest energy. So we can also look at our periodic table, and when we go across, this is our first energy shell, this is our second energy shell, this is our third energy shell, etc., etc. And we can do our orbital diagram or electron configuration that way. And we know that over here, if these are the s electrons, the s orbitals, over here are the p orbitals, and over here are the d orbitals, and here are the f's. So we know going from left to right, we can get our ordering from just looking at the periodic table. So first, for example, doing the 1s, we know, okay, for energy level 1, we can have an s orbital, and it can hold 2 electrons. Going down to the second row, we can have a, change my color, we can have the 2s, which can hold 2 electrons. But then we can go over here and see in row 2, these are the p blocks. So we can also have 2p. Coming down to the next row, we can have 3s. Going across directly from where we are, we then have the 3p. Coming down to the next row, now we have the 4s. But before we can get to the 4p, we have to go across this block here, which are d orbitals. And these happen to be the d orbitals from the period right before this one. So since this is period 4, these are the d electrons for period 3. So therefore, those are the 3 d electrons that fill next. Now we're going to go back to the period 4 electrons, which are the 4p. And it's the same on and on. So one more time, as we go to 5, we have our 5s. Going across here, now as we continue across, these are the d electrons. So They're not in period 5, they're actually in period 4. So whatever period you're in, the d electrons in that period are going to um, you subtract 1 from the period number. So the d electrons here are going to be 4 d electrons. And then as we continue on across, these p electrons are 5. So that's on the filling order. And we can look at the periodic table and determine that, or we can look at our chart and determine that. But it's a lot easier and quicker if you can get accustomed to looking at the periodic table and identifying um, the filling order. So let's look at our first example, which is selenium. And let me see if I can erase all of this. Okay. All right. So I'm going to put my numbers back on the periods. All right. So now let's look at the example selenium. Selenium is located right here on the periodic table. So therefore, we can look at the position that it's in and know that period 4, we see that period 4 has the s electrons filled. It has the 3d electrons filled. And then we're going to continue over. So the last orbital that's filled here is the 4p. Like I say, this is how we use the periodic table to do this. You can also just use your chart and just fill up electrons until you get to 34. Okay, so let's do our orbital diagram notation. All right, so since we know that all of the rest of these are filled, we can just go ahead and put 2 electrons at a time in each orbital. Each p orbital, there's 3 of them. And now we're down here. So we're back at the 4s. And we know that we then go to the 3d. Each d orbital, we have 5 orbitals. They're completely filled up, so we can go ahead and put them all in. And so now, at this point, we've made it across the period. We are here at the d orbitals. So now we go back to the 3p, I'm sorry, the 4p orbitals, which there are 3. And so now, we're not going to completely fill up this orbital because selenium lies right here. So now we're going to have to put the remainder. This is 30 electrons total up to this point. So now we've got the remaining 4 that we've got to put in the p orbital here. And so we're going to do it individually first, remember. 1, 2, 3. And these have parallel spins. And now to put the last one in, we're going to come back and start pairing. And it's going to be with an opposite spin. So that's what your orbital diagram notation should look like for selenium. Remember, we can take the shorthand notation for selenium or for any element. We look at the noble gas that is in the period right before it. And in this case, it's argon. Argon has 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. The argon is in period 3 and it has its p orbitals completely filled. So we can just, without having to rewrite all that, we can just say that this configuration that I have here highlighted in green is equivalent to argon. And now we can just write the remaining orbitals here. Um, the same exact way. Okay. So that shorthand notation allows us to be able to save a little bit of time. So both ways are correct ways of writing orbital diagram notation for selenium. Either we write it out the long, long way, um, like we did here, or we write it out the shorthand way like we did right here. Okay, so that's selenium. I'm going to leave our order up here because this is always going to be the order that our electrons fill in, and then we're going to move on to the next example, which is chlorine. I'm going fast here, so you have the opportunity to just press pause if you need to have more time to write down what I just wrote. Okay. And so the next couple of examples are going to go a lot faster because the first couple of examples I used to explain the strategy. And so this one is going to go a lot faster. So chlorine is located right here on the periodic table, and chlorine has 17 electrons. All right, so chlorine has 17 electrons, but what we actually are asked to find the orbital diagram notation for is the chlorine anion, Cl minus. So since chlorine, the neutral atom, has 17 electrons, anytime we have an anion, we know that we have to add an electron. So the chlorine anion has 17 electrons plus the 1 electron that we have to count for the charge, the -1 charge on chlorine. So therefore, we have a total of 18 electrons. So there's a couple of different ways, once again, that we can approach if we want to just go and draw our boxes in the correct order and just fill them up until we get to 18 electrons. We can do that. And that would be like this. So drawing our boxes in the right order. 1s, we have 2 in there. We have 2s, we have 2 in there. We've got the 2p orbitals. There's 3 of those, remember. And we've got 6 in there. Let me draw that where you can actually see it better. So that's a total of 2, 4, 6, 8. That's a total of 10 electrons thus far. And so now we've got the next one is 3s. That gives us a total of 12 electrons. Then we go to 3p. And so we've got 6 electrons that we've got left that we've got to fill. So we put them in a 3p. There's 6 electrons. So that's a total of 18 electrons. So that's our orbital diagram notation for chlorine. minus, the chlorine minus, and the chlorine minus anion. So if you wanted to look at how we write the shorthand notation for that, we actually gained an electron here. So the number of electrons moved up to 18. So now chlorine looks exactly like this. The argon noble gas, which has 18 electrons. There's 18 electrons total here. So we can just simply represent this ion in shorthand notation like that if we need to. Okay. Alrighty. So that was where we so now let's look at the aluminum cation. The aluminum cation, Al3 plus. Okay, aluminum, the neutral atom, is right here on the periodic table. It has 13 electrons. In order to form the aluminum 3 plus ion, we know that we've got to remove 3 units of negative charge to get the positive unit. So that means we've got to remove 3 electrons. So we're going to end up with 10 electrons in the aluminum 3 plus cation. So when we do that, we could actually just look at the periodic table here and say, okay, when we remove these 3 electrons, we're going to be back right here. We're going to look just like neon because neon has 10 electrons. So it just looks like that in shorthand notation. I'm going to go ahead and write it out in orbital diagram in the long form. We've got 1s with 2 electrons there. We've got 2s with 2 electrons. And then we've got 2p that has 6 electrons. So that's a total of 10 electrons. And 10 electrons looks like that. Okay, so those are the 3 examples. One with the neutral atom, one that I did that has a negative charge, and one that I did that has a positive charge. I'll practice the rest of those. And if you have any questions or difficulties, then come and see me. Now, moving on to the next one. The next question asks us to write the element that corresponds to the following electron configurations. So, since we're identifying the element, we're assuming that we're not dealing with cations or anions because they specify that we are writing the element that corresponds to the following electron configurations. Therefore, we can just add the total number of electrons: 2, 4, 10, 12, 18, 26. And when we look at the periodic table and find the block on the periodic table that has an atomic number of 26, that corresponds to iron. And when you apply what you already know about how we can identify electron configuration by using the blocks in the periodic table, you can look and match this electron configuration up and see that it makes sense that this is the configuration for iron. The same is true when we look at the next one. When we add the total number of electrons up, we get 24. And we see that 24 corresponds to chromium. This electron configuration also is one of those exceptions that we saw in class to the normal filling order. As you can see, the 4s shell was not completely filled before moving to the D block, and that is also consistent with what we know to be true for chromium. Looking at one more here, let's look at argon. So when we add up the total number of electrons, what we need to do is find argon on the periodic table. And we see that the total number of electrons that argon has is 18. And then we add to it the remainder of the electrons in the valence in the outer shell. And so we get, pardon me, I think I misspoke there. Did I say outer shell? We add up the remainder of the electrons. And so we end up with 18 plus 10, which gives us a total of 28 electrons. And that corresponds to nickel. And once again, applying what we know about how to write electron configurations by just looking at the periodic table. Once you look at nickel's position on the periodic table, you'll see that that actually makes sense and correctly represents the electron configuration for nickel. Case in point, starting with the argon core, 4s2 here, and then 3d8. And the same was true for iron. How many core electrons and valence electrons are in the following? I'm going to do a couple here. We can get to this number in a couple of different ways. The way that I'm going to go with and show you is by just doing the shorthand electron configuration. And for silver, that is the krypton core with a 5s2 next, and then a 4d9. So when we identify valence electrons, we know that it doesn't matter what order the electrons fill in. We know that electrons fill from this order, from left to right. But when we identify the valence electrons, we're talking about the electrons that are in the highest energy shell. And so in this case, that would be the 5, period 5. So the 5 principal quantum number, 5 is the largest energy shell occupied, or the highest energy shell occupied. So the valence electrons are the electrons that are in that shell. So in this case, the number of valence electrons is going to be 2. So the number of core electrons if the valence electrons are 2, then the core electrons are going to be everything else. And so you can simply take the atomic number for silver and subtract 2 and get a total of 45 valence electrons. Or you can identify these 2 electrons as being valence electrons and then add the value of the krypton atomic number, which is 36, plus the remainder of the electrons that are not in the valence shell, and you also end up with 45. Okay, so that is core electrons and valence electrons in silver. So let's look at one of each of the other types. For this one, it's pretty easy to identify valence electrons because the highest shell occupied is 4. So there's one valence electron here. So the remainder of the electrons are core electrons. And when we count them up, there's 2, 4, 10, 12, 18. Okay. Once again, looking at these two, this one here, the highest number is 3. So we add up the total number of electrons that are in the third energy shell. And so that is going to give us valence electrons, which is 7. The core electrons we get, okay, here we go. The core electrons we get by looking at the neon on the periodic table, seeing that it has 10 electrons in it. This one, valence electron is equal to 2, because 4 is the highest energy shell occupied. The core electrons in this case are going to be equal to argon core, which has 18 electrons, plus the remainder of the electrons, which are 8 more, so it's 26. And each time, in each case, the total number of electrons, valence and core, should equal the total number of electrons we started with. So we started with 28 electrons here. In the valence shell, we have 2. In the core shells, we have 26. Over here, we started with a total of 17 electrons, and there's 17 total. So the last one we'll do is, let's look at aluminum 3+. Aluminum 3+ has an electron configuration that looks like neon. So the number of valence electrons is going to be 8, and the number of core electrons is going to be 2, because that ends up being a total number of 10 electrons. once you take the atomic number for aluminum, which is 13, and you know you have a positive charge of 3, so that means we're going to be removing 3 units of negative charge. So that means we're removing 3 electrons, and that gives us a total of 10 electrons. And that corresponds to a shell, outer shell that looks exactly like neon, or an outer shell that has 8 electrons in the valence and 2 electrons in the core shell. When you look at chlorine, I'm going to leave the rest of them for you to do, but when you look at chlorine and sulfur, rather than subtracting electrons, I'm going to add 1 electron for chlorine and add 2 electrons for sulfur. Okay, the next question asks us to place the following elements in order of increasing atomic radius. So let's go look at the periodic table. So we know that atomic radius increases in this direction and in this direction. So let us figure out, look at the periodic table and find out where these elements are. So phosphorus is here, barium is down here, chlorine is right here. So if we're going in this direction from smallest to largest, then this is the direction that we can follow to place our elements in order of increasing size. So chlorine would be the smallest, phosphorus would be next, and then barium would be the largest. So we do that for all of these. One interesting one to note is the magnesium plus ion, and the magnesium 2 plus ion. Well, we don't need to look at the periodic table for that one because we know that anytime you remove electron density and form a cation, that the cation gets smaller with each removal of each electron. So magnesium, the neutral atom, would be the largest. So the magnesium 2 plus ion would be the smallest, followed by the magnesium plus ion, followed by the magnesium neutral atom. And the reason that is, remember we said that when you start out with an atom of a certain size, when you create a cation, each time you remove electron density, the first time you remove electron density, it gets smaller. And then as you continue to remove electron density, it gets even smaller. So this one has the largest amount of electron density removed. And this one has no electron density removed. If you use the same logic for the rest of them, you can get the order of increasing atomic radius. But remember, when we look at the relationship between different ions of different elements, then we'll need to consider what the final outer shell of the electron would look like. So let's take, for example, this bromium anion, the sodium cation, and the rubidium cation. And let's look at those on the periodic table. Okay, it's taking me a while to erase that. So first of all, for bromine, it's here. If we add an electron to it, that means it's going to look like krypton. So it would have a final size that would be about the same as krypton. Sodium is over here. To form the sodium cation, we would remove an electron, and therefore the sodium would end up looking like argon. And for the rubidium, it's down here. And if we remove an electron, it also is going to look like krypton. So, let me represent this where it's a little bit more clear. This is what the sodium ion looks like. This is what the bromine anion looks like. And this is also what the rubidium cation looks like. So therefore, if we're putting these in order of increasing atomic radius, when we look at where these trends take us, we're going down here. So therefore, the atomic size increases as we go in this direction. We cannot differentiate between bromine and rubidium, so we have to say that sodium is smaller than bromine, but bromine and rubidium are equal. The bromine anion and the rubidium cation are equal, but both of these are larger than the sodium cation. Okay. All right, so that's how we would approach looking at those types of problems. So let's go on to the next one. It's getting close to midnight, so I'm getting sleepy, so I'm going to try not to be confusing at all. Try to be as coherent as possible here. Okay, so the next one says represent the first ionization of sulfur and give the new electron configuration. So by definition, what is ionization? Ionization is the removal of an electron. Right? So if we remove an electron from sulfur, that means we're going to start with sulfur and end up with sulfur in the plus, because we removed the unit of negative charge. So we end up with sulfur plus that electron that we removed. So that's what it would look like when we write the first ionization of sulfur. So if we were to do a second ionization, we would start with this and remove an additional electron. But it only asks us for the first ionization here. Okay, so what is the new electron configuration? So for sulfur plus, sulfur, the neutral atom of sulfur has an atomic number of 16. So when we remove an electron, that gives us an atomic number of 15. So that's 15 total electrons. So the new electron configuration would look like neon, and then 3s2, 3p, 3. Okay, and the next one asks us to represent the second ionization of ruthenium and give its new electron configuration. So if we're talking about the second ionization, that means that ruthenium has already had one electron removed. So therefore, it starts out as ruthenium plus. So for the second ionization, we would end up removing a second electron and end up with ruthenium 2 plus that extra electron that was removed in this second ionization. So looking at ruthenium on the periodic table, we have an an atomic number of 44. And so with 2 electrons removed, there therefore are 42 total electrons. So we started out with 44. So we're down to 42. And we represent the electron configuration with the krypton core 5s2. The krypton core has 36 electrons in it. This is 40. And that will be 42. Okay, so that's it for that one. All right. Now the next question asks us to place the following in order of increasing ionization energy. That's what this IE1 means. And remember, IE1 and IE2 are different. IE1 is the first ionization energy. IE2 is the second ionization energy. The same way we just saw in the example we did previously. The first ionization energy is the energy that's required to remove the first electron from a neutral atom. The second ionization energy would be the energy that would be required to put in to remove the second electron. So this one asks us to put the following in order of increasing ionization energy. So we know on the periodic table that ionization energy increases in this direction. So let's go to the periodic table and do a couple of these. So the first one is nitrogen, fluorine, and arsenic. So nitrogen is right here, fluorine is right here, and arsenic is right here. So we're told what we know, that ionization energy increases as you go up and as you go to the right. And that it is incredibly difficult to remove an electron from a noble gas. Almost impossible. Okay, so we follow our trend over We know that we get larger as we go in this direction. But these two cancel each other out. So we would say that increasing ionization energy, the smallest is nitrogen, which is smaller than fluorine. And fluorine, you can't really distinguish based on its position in the periodic table between fluorine and argon. They're about the same. But based on what we know about noble gases and their incredibly stable electron configuration, we could probably safely assume that because this outer shell is completely full, it does not want to be disturbed, we can pretty safely assume that this would be the highest um, energy requirement to remove an electron from that. But based on the trends on the periodic table, the fact that when we go in this direction, we're supposed to get larger, but when we go down here, we get smaller, they kind of cancel each other out in terms of what we see as a trend based on the definition that we got in class. Okay, so you follow the same logic for the other two questions on this problem. Okay, the next question asks us to give the ground state configuration for the ion of the following. So if it just gives you the element and asks you to give the electron configuration for the ion, that means that it is expecting you to be able to identify, based on its position on the periodic table, what its most stable ion should look like. So we know that magnesium on the periodic table is in group 2. So therefore, it would want to lose 2 electrons to look like a noble gas. And therefore, you would remove 2 units of negative charge. So you would end up with a positive 2. Chlorine, on the other hand, is in group 7 on the periodic table. It lacks 1 electron to look like a noble gas. So what it would more than anything like to do is gain an electron to look like a noble gas. It wants to gain 1 electron. So you subtract its number, which is group 7 on the periodic table. You subtract 8 from that, and you get a negative 1. On the other hand, for oxygen is in group 6. So when you subtract 8 from that, you get a negative 2. Let me rewrite this. Negative 1 here. Negative 2 here. So what we simply do, just like we did with the other electron configuration problems, is look at the atomic number for magnesium on the periodic table. Which is 12. Subtract 2 from that because you removed 2 electrons. And now you have 10 electrons total. And that gives you 1 s2, 2 s2, 2 p6. And that's the same thing as neon core, a neon shorthand configuration. All right, and you do the same for the other two. In this case, chlorine has an atomic number. I think we already looked at chlorine and oxygen in our very first problem. They're ions. I think we looked at those already and did orbital diagram notations for those. So we saw that for chlorine, you would add an electron. It has an atomic number of 17. You would add an electron to that one, and you would end up with 18 electrons. And then you could write the electron configuration. And the same for oxygen, which has 8 electrons. When you when you add 2 to that, you end up with a total of 10 electrons. And in the end, all of these are going to look like the noble gas that it's trying to achieve the same electron configuration of. This is going to be argon. So this is a shorthand notation, but if you write the ground state electron configuration for the ions, you can, this one is for the magnesium ion. You could write it out, or you could write the shorthand notation. And I have written the shorthand notation for the chlorine ion. Uh-oh, wow, sorry. I wrote the shorthand notation for the chlorine ion, which simply will look like argon. And I also wrote the shorthand notation for oxygen, which would look like neon. Okay. Write the reaction for the second electron affinity of oxygen. So ionization is the removal of an electron. And electron affinity is just the opposite of that. It is the acquisition or the addition of an electron. So the second electron affinity means that oxygen has already gone through a first electron affinity where it has gained one electron. So now the second electron affinity will simply look like this. We start out with oxygen that already has an extra electron, and then you would add one here plus one electron, and you would end up with O2 minus. And that's it. Okay. This one asks us to place the following in order of decreasing metallic character. So once again, we have a trend that we can identify based on our definition from class that metallic character increases in that direction. So therefore, we can identify where these are on the periodic table. We've got phosphorus here. We've got arsenic. And then we've got potassium. So following the correct order, if we increase metallic character from left to right and down, then we can assume that arsenic is least like a metal. Phosphorus is more like a metal, but potassium is most like a metal. So therefore, I got this backwards because it asks us for decreasing metallic character. This is increasing. So the correct order for decreasing metallic character would be potassium, phosphorus, and arsenic. So potassium is most like a metal, and arsenic is least like a metal according to our trend. Place the following in order of, okay, we just did that one. Give a set of 4 quantum numbers that could represent the last electron added using the Aufbau principle to the fluorine atom. So if we look at the fluorine atom, it has, look at the periodic table, it has 9 electrons. So drawing the electron configuration, actually the orbital diagram for fluorine, we have the 1s orbital, the 2s orbital. And remember, when we fill the 3p orbital, we have 5 remaining electrons to fill. So the Aufbau principle is the building up principle. When we fill this, we're going to go in this direction. We're going to fill them all individually first. So once we do that, that gives us 2, 4, 7. So we've got 2 more electrons to add. So now we come back and start pairing them up with opposite spins. So now this is a total of 2, 4, 6, 8, 9 electrons. And the last electron that we added was this one. So based on what we know about quantum numbers, the N is equal to 2 because it's in energy shell 2. The orbital that it's in is a p orbital. And we know the L value for a p orbital is 1. L value for an s orbital is 0. For p orbital is 1. D orbital is 2. And F orbital is 3, right? So since this electron happens to be in a p orbital, the L value is equal to 1. So within each set of orbitals, we have our m sub L value. And since our L value is 1, then the m sub L value we know can go from whatever that L is, which is 1. So we put a negative in front of that. It can go from negative that number to positive that number. And that number happens to be 1 here. And 0 would be in the middle. Counting integers upward. So the m sub L value here, this one is negative 1, this one is 0, this one is positive 1. So the m sub L value of the orbital that that electron is in is 0. Okay. And finally, we have a spin quantum number, which tells us whether our electron is flipped up or down. In this case, it filled last, so it paired. And so when it paired, we assume that it's a down spin. So generally, these can be arbitrarily assigned, but this one we'll represent as negative 1/2. So that is those are your quantum numbers. N is equal to 2, L is equal to 1, M is equal to 0, M sub S is equal to negative 1. Okay, it asks us how many electrons are in the unpaired electrons are in the ground state silicon atom. So I'm not really going to do that one for you because I think that I've done a whole bunch of electron configuration and orbital notation. But what you will do is you're going to draw the orbital notation. Excuse me. You're going to draw the orbital diagram. And then you're going to look for how many electrons are unpaired. in silicon. And if you have questions, then you can come in and check with me and we can talk about it. All right. The next question asks us to identify by stating yes or no whether the following sets of atoms have their valence electrons in the same shell. So let's look at the strategy involved in solving this problem. Lithium is, go back to yellow. Lithium is, why can't I go to yellow? Okay. Sorry, guys. All right, lithium is right here. Nitrogen is right here. And fluorine is right here. So we want to know if the valence electrons are in the same shell. So these are not transition metals. So the valence electrons are 2s2. I'm sorry, 2s2. I'm getting ahead of myself. The valence electron in this one is 2s1. The valence electron in this one is 2p. 1, 2, 3, 3. The valence electron in this one is 2p5. So, yeah, they all have the same energy shell, which is 2. Okay? And that's how you would answer the remainder questions. When you get down here, you know that you would have to consider the transition elements in period 4 and up. Okay? If that still poses a problem for you, come and see me. Okay. Identify whether the following are diamagnetic or paramagnetic. Okay. So our strategy in solving this one is to write the orbital diagram notation and look at whether or not you end up with unpaired electrons or not. Okay? You're just simply looking at whether or not you have unpaired electrons. All right. And this last one, I'm assuming it's the last one, may not be. It actually contains the following in order of interesting electron affinity. So we know we've got a strange trend when it comes to electron affinity. We know that in the alkali group that we have a very identifiable trend that electron affinity increases in this direction. We also know that generally, across a period, that electron affinity will increase. But for the most part, it's difficult to have a predictable trend for electron affinity within a group or column. It's difficult to say. So in this particular case, when you're looking to group something in order of electron affinity, then the strongest indicator of whether something is going to increase in electron affinity or not is if it's going to be in one, or if it's going to be going across a period. Because if you're looking at two elements that are going up or down in a group or family, then you're going to have more ambiguity. You have more difficulty in establishing um, a real pattern. So, having said all that, I'm going to go through one of these for you. I'm just going to use a different color. So let's identify where um, these elements are. So sodium is right here. Chlorine is over here. And magnesium is right here. I guess I'm doing the second one. So therefore, it's pretty easy to see the trend in this case. Going from this direction to this direction, we can expect the affinity, electron affinity, to increase. So therefore, sodium is the smallest. Magnesium is larger than sodium, but chlorine has the largest electron affinity. Okay. All right. The very last question asks you to identify or which ionization process requires the most energy. Okay, so this actually just draws on your being able to remember your definition of ionization energy. So based on that definition, we know that the first ionization energy has a certain value, but we know that the second ionization energy, which is the energy that is required to remove that second electron, is always higher than the first ionization energy. So this letter A represents removing the first electron here. We remove it. So that's the first ionization energy. But this one represents removing the second electron to end up with the sodium 2 plus ion. So therefore, since this is the second ionization energy, it will require the most energy. So that's the last example on your practice. And once again, please, if you're having difficulties, I didn't go through every single solitary one, but I tried to give you some basic guidance and strategies for solving these problems. So if you're still a little bit unclear about something, please come to my office and see me or ask me after class, and I'll be very happy to assist you in trying to identify where your weaknesses are. Okay?